Hello everybody. I'd like to talk about some properties of cosets. So we'll use those properties of cosets to prove Lagrange's theorem. Lagrange's theorem says that if G is a finite group and H is a subgroup, then the size of H divides the size of G. So last time we saw a couple examples of that. Here's the group Z mod 30 at the top, and beneath it are listed all of its subgroups and their sizes, 15, 10, 6, 5, 3, 2, or 1, all divide 30. Another example is S3, the group of permutations of 3 elements. Well, S3 has size 6, which is 3 factorial, and its subgroups listed below have size 6, or 3, or 2, or 1, which all divide 6. Okay. But before we talk more about Lagrange's theorem, let's first focus on cosets and their properties. So I'm looking at this definition of cosets of H and G. So G is a group and H is an arbitrary subgroup of G. Now for any element A in G, we're going to define the left coset of H containing A as this collection, this set. So AH, A capital H, has as all of its elements a little h, where little h is in my subgroup. So what I'm doing here is I'm taking A and multiplying it by an arbitrary element, little h, of my subgroup. And those things, those products, A times little h, are the elements of my coset, A capital H. As an example, here I've drawn the group Z12. I've drawn its 12 elements just as dots here. So 0, 1 up through 0, 1, 2, 3, 4, all the way up through 11. Those are my elements of this group Z12. I've just drawn them as dots. Down below, I have the 3 different cosets of H, where H is the subgroup generated by 3. So H is the subgroup generated by 3. Its elements are 3, 6, 9, and 12, which is 0 mod 12. So up above is G. It has 12 elements. The first row below is H. It has 4 elements. Its cosets are drawn here. 0 plus H is H itself. 1 plus H is this coset. And 2 plus H is this coset. When we have here 0 plus H, this is AH, where A happens to be 0. And I've written a plus there because this is an additive group. Okay. Similarly, 1 plus H, this is AH, where A is 1. And the plus I've written because this is an additive group instead of a multiplicative group. And 2H is also AH. So for example, the elements of 1 plus H are all things of the form 1 plus an element of the subgroup H. Well, the elements of the subgroup H are 0, 3, 6, and 9. And if I add 1 to those, I get 1, 4, 7, and 10. Okay. And some things that you'll notice about these 3 cosets. So all 3 cosets have size 4. Another thing that you'll notice is that the 3 cosets are disjoint. So no element is in more than 1 coset. All right. And you'll also notice that the cosets partition the elements of the larger group. So every element of the larger group is in exactly 1 coset. Okay, it's in a coset, and furthermore, it's in exactly 1 coset. All right. So let's talk about some of the properties of cosets a little bit more rigorously. And then afterwards, we'll use those properties to prove Lagrange's theorem. Okay, the first property that I want to prove about cosets is this first bullet. It's highlighted in green. And we're proving that A is an element of its own coset, AH. So let's prove this first bullet. What is AH? So it's important to remember definitions this class. The coset AH is the set of things of the form A little h, where little h is in my subgroup. Okay. So to prove that A is in this coset AH, I need to write A in this form, A times something in my subgroup. Well, what can I multiply A by to get A? Just the identity. And is the identity in my subgroup capital H? Yeah, the identity's in every subgroup. So I can say, since H is a subgroup, H contains the identity E. Okay, and then we can write A as A times the identity, which is just A times H, where I'm choosing my element of this subgroup capital H to be the identity. And therefore, since I've written A as A times something in my subgroup, namely A times the identity, that proves that A is in the coset AH. In other words, A is in its own coset. All right, now let's talk about the second bullet. The second bullet is saying that two cosets, AH and BH, either they're equal or they're disjoint. So here on the left, this is either these two cosets that are equal, or here, this is saying the cosets, otherwise the cosets are disjoint. They have no elements in common. In other words, their intersection is the empty set. So this symbol right here means intersection, and this symbol right here is the empty set. So the intersection of these two cosets is empty. In other words, they have no elements in common. We won't prove this together. You can try it out and let me know your questions. But let me just show you an example of this. So two cosets are either equal or disjoint. We see that here in these cosets of the subgroup generated by 3 and Z mod 12. So these three cosets are certainly disjoint. None of them have any elements in common. If I look at the coset 3 plus H, I get exactly this coset, 0 plus H. So if I take H, 0, 3, 6, and 9, add 3 to all those elements, I get 3, 6, 9, and 12, which is 0. I get the same coset back. 1 plus H is the same as the coset 4 plus H, it turns out. 2 plus H is the same as the coset 5 plus H. 0 plus H is the same as the coset 6 plus H. And this continues. So here are some examples of cosets that are equal. 0 plus H is equal to 3 plus H. Whereas these are some examples of cosets that are disjoint. For those cosets, no two elements are shared in common. Okay, let's talk about the third bullet point now. We'll prove this third bullet point together. So the third bullet point says that any two cosets have the same size. If AH and BH are two cosets, where A and B are just different elements of my group G, then they necessarily have the same size. Okay, so indeed, we'll show that the size of a coset AH is just the same as the size of the group H. Okay, and once we've shown this first equality, we've certainly shown the second equality, because A and B are just arbitrary elements of my group. Okay, so let's see why the size of the coset AH is just the same as the size of the subgroup H. Well, what we'll do is we'll again recall the definition of the coset AH. It's a set of things of the form A times little h, where little h is an arbitrary element of my subgroup. Okay. So the size of this set is at most the size of H. Do you see that? Every different element I choose in little h gives me at most one different element here. So, I'm only changing h over, I'm only changing little h over a certain number of different variables, which is given by the size of the subgroup capital H. So I can only vary little h over the size of capital H different things. So I can only get at most capital H different outputs here for A times little h. And now we want to show that, to see that the size of the set is equal to the size of capital H, we need to show that no two elements, A times little h, or A times little h prime, where h and h prime are in capital H, collide. We need to make sure there's no collisions. Okay, so to see this set has size exactly the size of the subgroup H, note that if A times little h were equal to A times h prime, for h and h prime in my subgroup capital H, then by cancellation, right, cancellation allows me to sort of cancel here. We get h equals h prime. Okay, so hence the size of AH is equal to the size of H. What we've shown is that as we vary H over all elements of the subgroup, we get, of course, at most, the size of H different outputs for A times H. And furthermore, this sentence is showing that we get exactly that many different outputs. Because oops. Oh. I'm having a tablet brain fart, but to see that we get exactly the size of H different elements, note that two terms, AH and AH prime, collide only if H and H prime were equal. So as long as H and H prime are distinct, you get different things, AH and AH prime. So that shows that the size of the subgroup is exactly equal. The size of the coset AH is exactly equal to the size of the subgroup H. All right. So those are three very important properties about cosets in the bullets above. And now let's use those properties to prove Lagrange's theorem. All right, so remember, we're proving that if G is a group and H is a subgroup, then the size of the subgroup divides the size of the group. Furthermore, the number of cosets of H in G will be that fraction, size of G divided by size of H. All right, so we're going to let A1H up through ARH be the different cosets of H in G. So in the case where G was Z12 and H was the subgroup generated by 3, then we had 0 plus H, 1 plus H, and 2 plus H as the different cosets. So R there was 3, right? In this example, R is 3 because I have 3 different cosets. All right, so A1H through ARH are the different cosets of H and G. By this first bullet above, each element of the group is in some coset. A1 is in this coset A1H. A2 is in this coset A2H. AR is in this coset ARH. And any element of G is in some coset. So maybe B is some other name of an element in G. Maybe B is certainly in the coset B times H, and the coset B times H might be equal, for example, to A2 times H. All right. So that means that every element of G is in one of these cosets. So G is the union of all of those R different cosets. The second bullet point up above, this one, says the cosets are either equal or disjoint. Well, they're not equal because I wanted these cosets to be the distinct cosets. So these cosets, A1H through ARH, are all disjoint. And so that means they have no elements in common. In this union, no things collide. Okay? So when you have a union that happens to be disjoint, the size of the union is just the sum of the sizes of the individual pieces. So the size of G is in fact the sum of the sizes of all these disjoint pieces. Okay? And now finally we'll apply the third bullet above. The third bullet says that all of the cosets have the same exact size. What is that size? You'll remember that size is just the size of the subgroup, H. So each of these terms on the left-hand side have the size given by the size of H. Those each have this size right here. And how many do I have on this left-hand side? I have 1, 2, 3, 4, all the way up to R of these pieces. I have R pieces, all of size, the size of H. Okay, so the size of the left-hand side of that equation is just equal on the nose to R times the size of H. Okay. So in summary, the size of the group is just equal to R times the size of H. So from this equation, we certainly get that the size of H divides the size of G. Right? From this equation, certainly you see that the size of H divides the size of G. And what is the remainder, or what is the quotient? So what is this fraction, the size of G divided by the size of H? It's this integer number R, which is the number of cosets of H and G. So we've proven Lagrange's theorem. We've proven that the size of a subgroup divides the size of the group. And furthermore, the number of cosets, R, down below, is equal to that ratio, the size of G divided by the size of H. Let me end this video by saying that just because some number divides the size of a group doesn't mean that there's a subgroup of that given size. So A4 is this group of size 12, 6 divides 12, but A4 does not have any subgroups of size 6. Okay. So the converse to Lagrange's theorem is sort of not true. If you have a subgroup, then the size of that subgroup divides the size of the group. But just because you have a number that divides the size of the group, that doesn't mean that there's a subgroup of that specified size. All right. Thanks for your attention, and let me know if you have questions.